Transformations of periodic functions. So let's just review when you're looking at transformations, and we're going to be looking at all of them in this lesson. It says, given y equals f of x, describe in words the transformations that occur to the graph of y equals 3 f of 2x plus 30 and then minus 4. Now remember, when you are looking at transform functions, that the horizontal stretch or compression does need to be factored out. So the coefficient of x needs to be in factored form in order for you to be able to describe the transformations. So here you'll notice that I've actually factored out the coefficient, and I have y equals 3 f of 2 bracket x plus 15 minus 4. Now once you have this in factored form, you should be able to describe the transformations. The number at the in front of the f and the number that's being added or subtracted at the end represent your vertical transformations, and the numbers inside the brackets where the x are represent your horizontal transformations. So in this case, I have a vertical stretch by a factor of 3, a horizontal compression by a factor of a half. Remember, it's always a reciprocal. So the number I'm actually multiplying the x values by is a half, so that tells me it's a compression. A horizontal shift to the left, 15 units, and a vertical shift down, 4 units. So just to summarize, when you're looking at vertical translations or vertical shifts, when you're looking at trig functions, if you have y equals sine theta plus a value, or y equals cosine theta plus some value, that represents a vertical shift up or down. So this just says trig theta, but that can be sine theta or cosine theta. It doesn't really matter which one. And vertical translations are determined by the value of c. If c is greater than 0, then the graph shifts up c units. If c is less than 0, then the graph is shifting down c units. And to graph this, you're going to move all your key points up or down c units. Okay, so let's take a look at an example of a graph that has a vertical translation in it. And so it says, describe the transformations and then graph the following. And so if you look at the equation here, we have y equals 2 cos x plus 4. And in this case, you have two numbers that are affecting the base cosine function. And the first number is a coefficient of 2, which means the graph has been vertically stretched by a factor of 2. And as you know, as you stretch a graph vertically, the amplitude of the graph changes, so the maximum and minimum values will change. And you'll also notice that you're adding 4 at the end, which means that this is a vertical shift up 4 units. So there's a description of the transformations. Now when you are graphing this, the first thing you want to think about is what the period of the cosine function would be. And because it hasn't been horizontally stretched or compressed at all, I know that the period of the function is still 360 degrees. So now I want to think about what the amplitude is. The amplitude of this function, because it's been vertically stretched by a factor of 2, the amplitude in this case is 2. So what that tells me is that the maximum value is going to be 2 so far, and the minimum value is going to be -2 when I actually graph this. Okay? But then, because the graph has been shifted up 4 units, what that means is all my values are going to move up 4 units. So that means the maximum value is going to increase by 4, and the minimum value is going to increase by 4 as well. So what that actually means is that my maximum value for my graph is going to be at 6, and my minimum value is actually going to be just at 2. Okay? So what we're going to do is we're going to graph 2 cycles of this graph. The first cycle will be the base function with just the vertical stretch, and then the second graph, which is the one that I'm actually looking at, and that I want, is going to be the one that's been shifted up 4 units. So what I'll do is set up my scale here. And so this is -1, -2. This is 1, 2, 3, 4, 5, and 6. And because one period of the function is 360 degrees, just going to label this quickly. Because one cycle of the graph is 360 degrees, I want to make sure that my scale here goes up to 360, and then I'm going to split the scale and then split it again, and so that tells me my scale is going to go by 90. So 90, 180, 270, and then 360. Okay, so because this is a cosine function, I'm going to graph y equals 2 cos x first, and then I'm going to shift the entire graph up 4 units. So it's a cosine function, so I know it starts at a max and it ends at a max. and it's going to have a min in between, and then my two zeros, 0 and 0. And I'm going to just draw this graph dotted because this is not actually the graph of the function that I want. The function that I want has been vertically shifted up 4 units, and so I'll use a different color to show that. And so what that means is my maximum values have moved up 4 units, so they move from 2 up to 6. And that'll be true at the beginning and at the end of the cycle. And my minimum value has been shifted up as well, so that's going to move down from -2 up to 2. So it's going to move up to 2. And my zeros have also moved up, and the zeros have moved from 0 up to 4. And so you should notice the same kind of graph. And now if I sketch a curve, and this one's going to be a solid one because this is the graph I actually want. There's the cosine function shifted up 4 units. So this is y equals 2 cos x plus 4. Okay, so vertically stretched by a factor of 2 and shifted up 4 units. Okay, just to summarize horizontal translations. So horizontal translations are inside the brackets where the angle is. So this would look like, if you look at a sine function, this would be like y equals sine of x plus, I don't know, 90 degrees, or y equals cos of x minus 45 degrees. That's what it would sort of look like. It would be inside the brackets. And so horizontal translations are determined by the value of d. In trig functions, a horizontal translation is called a phase shift. So that's what we're going to be calling it. And if d is greater than 0, the graph shifts right d units. And if d is less than 0, graph shifts left d units. And to graph this, we're going to move all the key points left or right d units. So that's exactly the same as what we've looked at from before. Okay? So let's look at an example that has a horizontal shift or a phase shift incorporated in it. And so example 2, we're looking at describing the transformations and then graphing the following again. And now this time, because this is a horizontal shift, or in other words a phase shift, this is actually a phase shift to the left 90 degrees. Okay, so that tells me that the graph is going to move to the left 90 degrees. So if you actually look at the axes that I've drawn here, I made sure to leave a little bit of extra space here on the left hand side because I'm eventually going to take the graph that's here and shift it a little bit to the left. Okay, so similar to what we did previously, we're going to start by stating the period of the function. And because there's no horizontal stretch or compression, I know that the period of the function is still 360 degrees. And in terms of the amplitude, because the coefficient here is still 1, I know that the amplitude is still going to be 1. So that tells me my max and min values are not changing. So I'm going to start by setting up my scale. So let's say this is at 1 and this here is at -1. The period of the function is 360 degrees and I'm only drawing one cycle, so I know it's going to take up to 360 degrees. And I'm going to split up this scale, or this one cycle, so I know one full cycle of the sine function is going to go from 0 to 360. And what I'm going to do is I'm going to split this in half and then split it in half again so that I can get my scale. So this would be half of 360 is 180. Half of that is 90. So I'll have a key point at 0, 90, 180, 270, and then 360. Okay, and try your best to try to evenly space it so that it's not like, so that 90 is not this wide and then 180 is a little bit bigger than that. You want to try to make sure that you're using a pretty balanced scale. And so what that means is if I'm graphing the sine function, I'm going to start by just graphing sine x. The second graph that I draw is going to include the shift. The first graph that I draw is just going to be the base function. So a sine function starts at a 0, ends at a 0, has a 0 in the middle, has a max between the first two zeros and a min between the last two zeros. And if I draw a quick sketch of the sine function so far, that's what it would look like. But the sine function I want has been horizontally shifted to the left 90 degrees. Okay, or phase shifted to the left 90 degrees. So what that means is I actually need to add a little tick mark here and go to the left -90, just following through with the same scale that I had on the right hand side. And all my key points are going to shift to the left 90 degrees. So I'm going to start with my zeros, and I'm going to shift all my zeros to the left 90 degrees. Then I'll look at my maximum and move that over, and then I'll look at my minimum and then I'll move that over. So the first zero I had here has moved to the left. Second zero also moves to the left 90 degrees. And the last zero also moves to the left 90 degrees. So there's where all my new zeros have gone. The maximum value I had that was at 90 and 1 is now going to shift to the left 90 degrees. And the minimum value that I had here is going to shift from 270 to the left up to 180. And you'll notice that the points still follow the same trend. And if I sketch a curve through the points, you'll notice that it ends up creating the same graph but shifted to the left 90 degrees. Okay. What you should also notice is because the graph has been shifted to the left, what it ends up affecting is the domain of the graph because it's been shifted to the left. Okay. Okay, vertical reflections, just to summarize vertical reflections, we're not going to look at horizontal reflections, just focus on vertical reflections. And so vertical reflections, if you have y equals negative trig theta, so this would look like y equals negative sine theta or y equals negative cos theta. And the graph of y equals negative sine is the graph of y equals sine reflected in the x-axis. And same thing with the cosine graph, it's reflected in the x-axis. And so it's actually really easy to graph reflections. What ends up happening is the maximum values become the minimum values and the minimum values become the maximum values. So if you had a graph that looked like, let's say you had a sine function, the reflected one, the max would become the minimum and the minimum would become the maximum, and so you would end up having this as a reflection.